Oh, hi there. It's Mrs. Bertrand, and this is Ionic Bonding. So why do atoms even form bonds? The whole point of atoms forming bonds is so they can become stable. And stable just means that they're going to fill their valence electron shell with electrons. In the main group elements, so the two towers, a filled shell is usually an octet. An octet means 8. That's not always the case, but almost always the case. So 8 electrons is usually our goal. So when we're thinking about bonding, we're thinking about, in terms of ionic bonding, gaining and losing electrons to make a filled shell of 8. If we have a metal and a non-metal, this is an ionic bond. So the metals are the losers. They're going to have a few electrons only in their outer shell, as you can see from this Bohr-Rutherford picture. Magnesium, as you know, is in column 2. So it has 2 valence electrons. Notice that if it was able to lose those 2 electrons, the shell underneath is nice and full. So that means that magnesium wants to lose 2 electrons to fill its shell. Also notice why it would become positive. Right now it has 12 negative electrons and 12 positive protons, which means 0 charge overall. But if I take away 2 electrons, then it's going to only have 10 negative electrons. It will still have its 12 protons, so it's going to have a positive 2 charge overall. So that's why losing electrons makes a positive outcome. Having a look on the flip side, the other half of an ionic bond, we have our nonmetals. They're the gainers of electrons. And again, this makes sense if we have a look at our Bohr-Rutherford picture, because we can see quite easily that there are 2 places where electrons want to be gained to fill that shell. Again, when they gain electrons, they're going to become negative. We're gaining negative electrons, so it should make sense that, okay, we're gaining electrons are negative. But have a look at the proton-electron story as well. So right now, if we have a regular atom, we have 8 negative electrons and 8 positive protons for a no charge, a neutral atom. However, if I'm gaining 2 electrons, I'm going to have 10 negatives and still 8 protons. So I will have a negative 2 charge. So it's all about the protons versus the electrons that are on the outside here. So a couple of definitions. An ionic bond is the attractive electrostatic force between a negative and a positive ion. So it's the negative and positive, those opposite charges, that make ionic bonds stick together. And an ionic compound is a chemical compound composed of ions held together by ionic bonds. So we're going to start with the easiest type of ionic bonding, which is called binary. And binary just means 2. So when it comes to 2, we're going to have one type of metal, that's the first thing of the 2, and the second is a type of non-metal. It doesn't mean 2 ingredients in total. You can have multiple metals and multiple non-metals, but they have to be of the same type, and you'll see that when we make some formulas. Let's start with naming though, because naming is the easier of the 2 parts of the story. So as we know, our ionic bonds have metals and non-metals. The metal name stays the same. You're just going to read that off the periodic table and copy it down. The non-metal, however, you're going to change its ending. So this is where it gets a little bit tricky, because you have to take off some of the existing ending to put this new ending on. This new ending is an "-ide" ending, and it will take a little bit of practice to see how that works out. Let's try these 2 examples together. So our first one is Na2S, and as I mentioned before, you can have in a binary compound 2 different elements, but you might not have just one of each. In this case, we have 2 sodiums. We'll make sense of that when we make formulas in just a minute. But let's practice our naming rules. So our first element is always the metal, so the metal always stays the same. So our element here is called sodium, and we can just look for that formula in the periodic table and read it off. Sulfur here is going to have to change to sulfide. So sulfur becomes sulfide. And you can spell the "fide" with a PH sound. That's, I think, the Canadian spelling. And then there you can also use an F. I think that's the American spelling. You can interchange them. I'm not fussy. Let's try the next one. We have a K. K is our metal, so we're just looking for that on the periodic table and writing it as is. So that is potassium. And then our second one there is phosphorus. And phosphorus becomes phosphide. That's probably one of the trickier ones, actually, to figure out how much do you chop off, but that's how much you chop off that one. All right, let's flip it over to making formulas. This is definitely the harder part of things. And this is where we want to make sure that the valence electrons are all full for each element in the problem. And we also need to make sure that the number of electrons lost is equal to the electrons gained. So in this case, for instance, we have 1 valence electron for sodium, and chlorine has 7. So you can see that if sodium gives away that electron, it now becomes a nice full shell, because underneath that 1 valence electron, if we think of our Bohr-Rutherford pictures, they have a nice full shell. So sodium is happy by giving away 1 electron, and chlorine of course has 7, so when it gets that electron, it's also going to be happy. So when we make a formula of sodium and chlorine, sodium chloride, a sodium chloride is just 1 of each. So there's our sodium chloride. However, this is not always the case. So let's consider this example where we've got magnesium and chlorine trying to come together. So we want to make a magnesium chloride now. As we can see here, magnesium wants to lose 2 electrons. It's got 2 valence electrons, being in column 2 of the periodic table, but chlorine only has space for 1. And so chlorine is happy if it gets 1 of magnesium's electrons, but the magnesium will not be happy. So how do we work it out when they don't have the same ratio of lost and gained? We're going to do a Lewis dot picture, and then I'm going to show you a shortcut method, because nobody wants to draw these pictures out, as I'm going to show you. So again, we're going to start with that picture of magnesium and chlorine. And we've got our 7 electrons around chlorine and our 2 electrons around magnesium. So we're okay here. Again, magnesium is happy to lose an electron, and chlorine is happy. But magnesium still is not happy. So what needs to happen next? Well, we're going to have to give chlorine, or more chlorine, to the picture, because magnesium needs to lose another electron. Now when it does that, magnesium is now happy, chlorine's now happy, the other chlorine was already happy, so we have 1 magnesium and 2 chlorines in this picture. Now, this puzzle wasn't too hard. I'm only involving 3 elements, but they can be more complicated. Like, they can involve like 5 or more elements in the picture. So we don't have to draw this out the whole time. So what we do is we do something called the crossover rule that allows us to do the exact same thing, but in a much shorter time. So I'm going to build up crossover rule for us. So the first part of making formulas is we're going to determine the stable ion for each element. So stable ion. This means that we're going to find the column number, we're going to find how many valence electrons the compound has, and then we're going to figure out what it would do to electrons. And it's the number of electrons lost or gained that is important here. Once I've got my stable ion numbers, because this is really about a number that I'm going to come up with. Again, this is the number of electrons that needs to be lost or gained in order for that element to become stable. Once I've got those special numbers, then I'm going to cross them over. So basically the 2 elements are going to swap numbers, and they're also going to cross down. So they're not going to be floating up. We're going to start with them up. That's how ions work. They put numbers up in the top right corner, but then we're going to cross them down. And that's called the crossover rule. So let's try it on for size. So we're going to start just by making that ion a couple times, and then we'll do crossover rule and put them all together. So starting with calcium, if I want to make the ion for calcium, I'm going to start with calcium's formula. So I'm going to look for it in the periodic table. And I find it right here. I'm going to circle it. And it's in column number 2. I know this periodic table is small, but bear with me. So here's what I need to do. First, I need the symbol for calcium, which is Ca. Then I need to consider what calcium will do to become stable. Because it's in column 2, it has 2 valence electrons. It's going to lose those 2 electrons for stability because underneath we'll have a nice full shell. So it will lose 2 electrons. That's where the 2 comes from, because it's lost 2. And because electrons are negative and I'm losing 2 negatives, I will now have an additional pair of protons that don't have that same balance. Again, if you want to repeat that lesson, that part of the lesson, go back to the beginning where I talked about that, but that's where the positive comes from. So that's the ion for calcium. Let's try one more. Let's do fluorine next. So fluorine is over here in column 7. So the starting place is the symbol for fluorine, and then thinking about what does it need to do to its electrons to become stable. So it has 7 valence electrons. It needs 1 more. So it's the number 1 we put in here because it's the number of electrons lost or gained to become stable. So fluorine needs 1 more electron. When it gains that electron, electrons are negative, so it will have a -1 charge. Okay. All right, let's do one more. So this one is nitrogen. Nitrogen is in column 5. Again, we start with our symbol. And then again, thinking about what does nitrogen have to do to become stable? It's got 5 electrons, its goal is 8, so it needs to gain 3 more. So again, 3 is the number because that's how many electrons need to be gained, and electrons are negative, so when they're gained, nitrogen will become more negative by 3. All right, time to put it all together. So we need those ions. We're going to make 2 of them this time, and then we're going to cross them over. So starting with sodium, we've got sodium, which is an Na. Sodium on your periodic table is in column 1, so it has 1 valence electron, which is going to lose to become a 1+ charge. Sulfide is sulfur. Sulfur is an S. On our periodic table, it's over in column 6. So it has 6 electrons already. It needs 2 more to become stable, so it's the number 2 we want. That's how many electrons it's going to gain. And when it gains, it will be a negative because gaining electrons, electrons are negative, so it'll become more negative. Again, the charges aren't as important, and if it's hard for you to remember positive, negative when you gain and lose, the first element is always positive and the second element is always negative. So you could just pattern it like that as well. At this point, I'm going to cross my numbers down, and we're basically swapping numbers. So in this case, I have sodium getting the 2 from sulfur, and sulfur will get the 1 from sodium. However, I never really write the number 1. It's not wrong to do that. You'll never see it done though. So sulfur, if we didn't have any, we would not even draw the S. So if you have an S, it's implying that you've got 1. Let's try another. We've got barium nitrate this time. So let's start with barium. So barium is in column 2. So it has 2 valence electrons. In order to become stable, it needs to get rid of those 2, so it's losing 2 electrons. That's where 2 comes from. Electrons are negative, so when I get rid of them, I become more positive. Nitride is nitrogen. So N, and we did this ion already, it's in column 5. 5 valence electrons, it needs 3 more to become stable. When it gains those 3 negative electrons, it'll be a -3 charge. Taking our numbers and crossing them over, we get a Ba3N2. One thing I didn't explain is that we don't do anything with the charge. The charge ends up evening itself out. We don't see it anymore. Here's why. I'll just show this to you so you understand why the charge disappears. Using the formula, we have 3 bariums, and each barium has a +2 charge. So that would mean a total of 6 positives. And then the nitrogen, there are 2 of them, and nitrogen has a 3- charge. So if I had 2 nitrogens, I would have -6. If I have then +6 and -6, those guys cancel each other out to make a charge of 0. So that's why in the end, whenever I'm doing crossover rule, I end up with no charge overall. All right, let's try one more. So let's try beryllium oxide. Beryllium is Be, it's in column 2. So it has 2 valence electrons. It's going to lose those 2 electrons to become stable. It is going to lose electrons, and electrons are negative, so it will be a +2. Again, if you don't remember that part, remember that the first one's always positive. Oxygen, oxide is oxygen, so O. It's in the 6th column, so it has 6 electrons already. It needs 2 more to become stable. Again, it's gaining 2 electrons. Electrons are negative, so -2. Taking our numbers and crossing them over and down, we get Be2O2. This example is interesting because it shows us one of the features of ionic bonding, and that is when you have things that are the same, or if you can reduce them, you are allowed to do so. So the more common way of writing beryllium oxide is BeO. This is always the way that we'll write it in a quiz or a test, or you'll see it in a textbook. It's not incorrect to keep the 2's, but it's more correct to get rid of them. That's always how it's done. And again, I've just made a subscript here. So you can always reduce to lowest terms. Another example might be, and you'll see this shortly, is let's say I had an x2y4. You could reduce this to an xy2, for instance, and take a common factor of 2 from each. So you'll see that happen as we go. All right, the next part of our bonding is called multivalent metals. And the multivalent metals are a group of metals that are in the transition metal area predominantly, and it's not predictable what their valence electrons are because they don't have column numbers that tell us that. So we use the back of our periodic table on the left-hand side to see some of these. They're not all there, but a lot of them are there, and so the ones that we're going to be using the most commonly are going to be there. We have two methods of naming multivalent metals. We have to have a system here because if you have something like lead, for instance, if you look on the back of the periodic table, lead comes in two forms. It's a lead with a 2+ or lead with a 4+. So I have to have a naming system to help me understand which one to use if I'm making a formula, or vice versa. If I have a formula, I need to recognize which type I'm using. So there are two different systems that are used. The stock system is the more up-to-date system, and it's used more commonly now, and so we use stock quite frequently. However, classical is sort of old school naming, and it's still being used. So until it gets phased out, we still have to teach that. So we're going to look at both options. We're going to do a little bit of work in classical. We're just going to make sure we know 5 elements in the classical style, whereas stock will use it for anything. We're going to start with stock naming first because it's a little bit easier and, again, more common at this point. So when we do stock naming, again, this is just a method for saying which of the charges or valencies, that's why it's called multivalent, which charge of the metal are we going to use, because it's not one of those main group elements where we can just look at the column number. It's one of these ones in the middle. So what we do is we use a bracket with Roman numerals to indicate the charge. So for instance, the example here, we put the metal name first, and then in between the metal and the non-metal, usually we would just have a metal and a non-metal. This is the new part. We're going to put those Roman numerals in between. So this just tells me that when I'm making this formula, it's almost easier when I'm making formulas because it's actually telling me the charge of the iron and I don't have to think about it. So it's saying, okay, when you make this formula, it's iron, which is the symbol Fe. That 3 there in the brackets is telling me it has a 3+ charge. And then chloride, same as always, I find it on the periodic table. It's in column 7, so it needs 1 more valence electron. And then, as usual, I'm doing my crossover to make my final formula. And there it is. You'll notice here that the symbol, and this happens quite frequently on the periodic table, the symbol for iron is Fe, which doesn't make any sense because iron starts with an I, but this is going back to its Latin roots, and this is where classical naming comes in, because a lot of elements on the periodic table were discovered before English was even a language, so they weren't named in the English language, they were named in the Latin language, which was the most common in that time for scholars. So in terms of classical naming, this is where those Latin roots are going to come out. So again, using our periodic table, the back left-hand side shows us a bunch of metals and what the possible charges are. In the classical naming, we're going to be using the classical name of the element. So the symbols will make more sense now because of those Latin roots. So it's kind of a Latin name for it. And then we have 2 possible endings for the Latin name. We have an us ending, which is telling us to use the lower of the 2 possible charges. To know what the charge is, we'll have to use the back of the periodic table to see the options. And then we also have an ick, and if we use an ick ending, it says, okay, use the higher of the charge. So for instance, again, going back to lead, lead is a 2+, or lead is a 4+. For lead, if I see the 2+, I would be using the us ending, or if I see the us ending is telling me to use the 2+. And then the ick ending would go with the 4+, which is the higher of the 2 charges. So this is a table that shows us the 5 that we should know. These are the ones that are most commonly used. And again, you'll notice that the names here are a little more in keeping with the symbol because that's where they come from. So for instance, iron has the symbol of Fe. Fe stands for ferrous or ferric, depending on which type. Tin has the symbol of Sn. That doesn't make any sense when we look at the word tin, but it does when we go to the Latin roots. Again, stannous or stannic, depending on if we've got the upper or the lower. So let's give it an example. I want us to make a stannic oxide. So we're going to be looking on the back of the periodic table to determine the higher charge for tin, because again, ick means higher charge. So looking back there on the periodic table, tin has the symbol of Sn. And the higher of the charge for tin is a 4+. This is not always going to be a 4+. The higher charge is the higher charge. So whichever element you're looking for, you've got to look at that one specifically. And then oxygen, we're looking on the front of the periodic table, just a regular old oxygen. So O, 6 columns, so 6 electrons, and we're gaining 2 to become stable, and then we're crossing over. Now, if we were paying attention, we know that this is actually not the best answer. It's fine, but it's not the best answer because we can reduce. So that's what we're going to do for our final answer. We're going to take a common factor of 2 out, and we will reduce it down to a 1:2 ratio. Same ratio, just lower form, and that's the more correct way. Let's do one more where we're naming. So here is our formula, and we want to use both stock and classical naming. So first we have to figure out what iron is and what type it is, and this is where we look at the crossover rule. So this 2 would have come from the iron, because remember when we do crossover rule, the numbers get swapped. So this tells me that I'm working with iron 2. So let's do stock naming first. Iron in brackets 2. Because I have to do both, I'm just going to put a slash here to save me some time, and I'm going to put the classical name for iron for the lower of the 2 charges. Again, I can use the back of my periodic table and look at both options for iron to know if iron 2 is the lower or the higher. It is the lower. Iron also comes as a 3+, that is the higher. So I need to call this one ferrous. That's my classical name. And then I'll just name the chlorine once, since that part would not change, and that one becomes a chloride. So we could call this an iron 2 chloride or a ferrous chloride. All right, moving on to ionic bonding with polyatomics and another piece called hydrated salts. A polyatomic ion is just a group of elements that have a charge, and they're on the back of the periodic table as well. They are on the right-hand side instead of the left, and most of them, you'll notice if you have a look at their names, most of them have 8 endings. So that's helpful because we just worked through the nonmetals, regular nonmetals on the front of the periodic table, and they're always ides. But the polyatomics are mostly 8s. So now I've got to watch out for those endings, because an ide means regular nonmetal and an 8 means go find a group on the back. There are some exceptions to the rule, and the most common ones are hydroxide, which has an ide ending, and cyanide, which has an ide ending. These are groups. If we look at the back of the periodic table, hydroxide, for instance, is an OH1-, and a cyanide is a CN1-, but almost all of them have those 8 endings. So if we see an 8, go to the back. Let's do a couple of examples for naming. The metal name stays the same as always, so we've got calcium there. Metal name stays the same. And then I've got one of those OH groups. Anytime I see a group, think back of the periodic table. That's where you're going to find its name. So when I look for it, we just saw it on the previous screen. This one is called a hydroxide. And I'm just going to write it exactly how I see it. The second one here, watch out. This is an iron compound, which means it's one of those multivalent. So I do have to use my multivalent rules in line with polyatomics. So I'm pairing those 2 skills together. So I'm looking across to see what kind of iron, because remember this would have come from the iron. So it's an iron 2 again. So I can call it an iron 2 or ferrous. We just did one like this. And then I'm doing the new piece. Anytime I see a group, once again, I'm going to look on the back of the periodic table. I'm looking for a PO4. And what I find is something called a phosphate. And again, I just write it exactly how I see it. In terms of making formulas, I'm going to use the crossover rule again. The one thing that I might have to do this time, however, is I might have to use a bracket. And sometimes it's really obvious when I have to use a bracket, and sometimes it's not so obvious. So if you're concerned, always put a bracket around your polyatomic to keep it as a group, and then you'll sort of avoid any issues with it. Let's have a look at this first example down below, our lithium sulfate. Lithium is a column 1, so 1 valence electron to lose, 1+ charge. And then I have an 8 ending, so I'm looking on the back of the periodic table, I'm looking for the word sulfate. I should see one called SO4, and it has a 2- charge. So again, I'm just going to cross the numbers over. I'm going to get Li2, SO4. I don't have to show the 1, so I can keep everything as is. But if you weren't sure about crossover, you could always put these brackets around the polyatomic first and then crossover. It is totally fine to keep a bracket here. I don't actually need it in this case because there's no number going beside it. But I could keep it in and it still would not change anything. So if you're not sure, put a bracket in and then cross over. Let's try aluminum dichromate. Aluminum, third column, so it's got 3 valence electrons to lose, becoming 3 plus. Again, I've got that 8 ending, so 8 says go to the back of the periodic table. There are 2 really similar names back here. There's a chromate and then there's a dichromate. There are 2 different things, so just be aware of that. Dichromate has the formula of Cr2O7 with a 2 minus charge. Again, if you want, put a bracket around this now because you aren't allowed to change this formula. Just like all the crossover we've ever done, it's just these numbers at the top that are crossing down. We don't get to change anything else. I'm just going to make some space up here for us so we can make a final formula. So when I cross over, Al will get the 2, and I'm going to keep this bracket in here because when I cross over and I want to add this number, I do want to say 3 groups, and so I do want the bracket to be there. If I did not have a bracket there, it would look like the 7 and the 3 were beside each other, in which case I would have 73 oxygens, which is nonsense. The last piece here that we want to talk about is naming hydrated salts. So this is an ionic compound that has water stuck in it. So a hydrate is just an ionic crystal with water stuck into this. And you will have experience with this if you've had like a pair of new shoes, for instance, and you get these little white packages in there. They're in there to absorb water, and they're just crystals that really like to do that, and they're called hydrated salts. So all we're going to do is we're going to name the ionic compound the way we always do, but then we're going to add the word for the hydrate. So we're going to say how many hydrates we have by using Greek prefixes. They are the same ones we use for covalent bonding, so we'll revisit these shortly as well when we do covalent bonding, but we're going to use them now to say how many waters are in the formula. These are the prefixes that you'll have some experience with. Again, we'll revisit these for covalent bonding, the same prefixes. We can go beyond 10, but we never do. So 10 is fine if you've got those 10. And when we're putting our formulas together, we're using our crossover rule as always. So the new piece here is not the ionic compound. We should have that under control. But the water piece that we're going to add in, we're going to put a dot between the ionic compound and the water molecule, and then we just put a number in front of the water molecule. Again, this is going to make sense when I show you in just a moment. So let's have a look at this first one. So we've got 2 pieces. The first piece is the ionic piece, and then the second piece is the water piece. Let's do the first piece first. So calcium, column 2. It's got 2 valence electrons, needs to lose those 2 electrons to become a 2 positive. Chloride is chlorine, 7th column. It's got 7 electrons, it needs to gain 1 more. So the first piece is just crossing them over to make a CaCl2. Now we're going to introduce the hydrate. Hydrate again just means water. Deca tells you how many waters. So using the table, we're going to put a dot in between, and then deca means 10, hydrate means water. So 10 H2Os, 10 waters. So that is our formula. Let's try the next one. We've got iron 3 nitrate. So let's do that piece first. Iron 3 plus, again the Roman numerals tell me that. I've got a nitrate. 8s are on the back, so I'm looking for the back of the periodic table, the word nitrate. Nitrate is NO3 with a 1 minus charge. Again, because I'm using a polyatomic, I'm going to put brackets in here before I do my crossover rule, so I don't make any mistakes. I'm going to have an Fe with a 1, don't need to show that. But then in the bracket, NO3 stays as it is, but there's a 3 coming across. Now I'm going to tackle this pentahydrate. So going to the table for prefixes, penta is 5. Hydrate just means water. So 5 waters, 5 H2Os.